Hello. This video is for chapter 1, which covers 8 sections. Don't freak out, please. The 8 sections are really, each section's about a page, sometimes just a paragraph, maybe 2 pages at most. So it's a very small chapter. There's no math chapter, and it's just getting your foundation set in some vocabulary words. So let me share my PowerPoint and we will run through chapter 1. So this PowerPoint can be found in your course content folder for this week. Let me get this in presentation mode. Okay. So we are looking at sections 1.1 through 1.8, and these are the sections we're covering. Again, this is all vocabulary and getting our foundation set for the rest of the semester. So statistics is quite different from algebra. Algebra, you are given formulas, you are plugging and chugging numbers and spitting out results. Most of the time, algebra is taught in a non-applicable way. And what I mean is that they don't actually show you when on earth you would ever use most of that algebra in real life on day-to-day tasks. Although we do use it every day, we just may not bust out an algebraic equation with X's and Y's in it in the middle of the grocery store to figure out a math problem, but you do use algebraic techniques when you are solving for everyday things. Statistics is quite different. Statistics is very applicable. In fact, everything in this course is going to be taught through application, and vocabulary is so important. Math, I believe, is its own language. So if you're learning Spanish for the first time and someone just starts speaking Spanish to you, you are not going to understand a darn word that they're saying. But if it's the same thing when we're talking about math, if I just spew out some math terminology to you without thoroughly explaining what on earth that means, I would not expect any of you guys to be able to understand or follow a math problem. So if you ever felt like you opened a math book and you're trying to read this math book and it makes no sense to you, well, there's a reason for that. You have to learn the language. So, reason of sharing that with you is so you can understand the importance of the chapters like these ones. We have some chapters where we're more focused on learning the concepts than we are number crunching, so to speak. There we go. All right, so the first part of this PowerPoint is going to be on sections 1.1 through 1.5. And then I actually broke up 1.6 through 1.8 in the second half of this PowerPoint. Data. What the heck is data? So data is essentially anything that we can collect. It's everywhere. Every single company produces data, prices of items sold in a store, profits made, in our own college, student retention. How many full-time students do we have signed up? Enrollment in classes, grades that you get. Literally anything can be data. And data can be categorized as many different aspects, and depending on what kind of qualities the data has will really make a difference in how we talk about the data, how we analyze the data, how we display the data, and what kind of techniques we'll use. Statistics, this is where we are, we're in statistics. It's a science. It's a science of data, essentially. So collecting and organizing and analyzing and interpreting the data in order to make these decisions of what to do next is what statistics is all about. It's all about data and what we can do with data. So historically, we have associated data with measurements and numbers that are purposeful and generated to help solve problems. So what constitutes data is changing. Okay, presently, the average smartphone user has about 3 billion bytes of data per month. And this number is growing rapidly, especially in the time that we're in. if you think about it, we're all on computers, we're remote, we're using the internet all the time. So this data is collected. Every single click you make on the internet is data. Okay, you wonder why you go on Amazon and Amazon knows exactly what you want to see? That's called recommender systems. Data was used to tailor your advertisements on websites specifically to you based on all the clicks that you click on the internet. So keep in mind, you are being watched. Everything's being watched. The word data in this context is different from the historical notion of purposeful measurement to solve a problem. Okay, so there are some data sets that we collect in order to make decisions and make meaningful uh, solving a problem. So for example, in a company, if I was to collect a data set of their sales and then I wanted to make a decision on what the company should do to better their sales, that's one type of data. Other data is just like these clicks on the internet. We're not necessarily collecting all the clicks you make on the internet to solve a problem. We're using it for other reasons, such as what is the most popular sites that people are using, what kind of people are clicking on certain sites, and tailoring your advertisements. Another category of data comes from the desire to create artificial intelligence, so like recommender systems, as I was talking about. The researchers confront the problem of reproducing human intelligence. They must solve the same data problems we do as humans and comprehending large volumes of visual and audio data, which is quite difficult. That's where AI kind of comes into play. An enormous amount of what is considered data in the quest for artificial intelligence are not even measurements in the traditional sense. So there's a lot of different types of data out there. We pretty much stick with tangible data in this class since this is a first class of statistics. And we dive into more complicated topics in our second class of statistics. If you'd like to take Stats 2 with me, which is exciting. If you do, you will not have to purchase another code for anything on the resources, Hawks Learning or our guru, as they are the same code. So you will be able to use this code in a Statistics 2 class if you take it with me. So um, let's move on. The meaning of data. So, the meaning of data, statisticians analyze data using pictures and summary measurements to build data driven predictive models. They develop methods of designing experiments and gathering data that are cost effective and diminish bias. Essentially, statistics is a formal way of thinking with data. So, taking a look at this graph, and I'll give you a minute to take a look and try to figure out what you're looking at before I run through an explanation. So, one of the things we need to do as little statisticians is we need to be able to read graphs. We need to be able to look at a graph and understand what story is this graph telling me. So, for this particular graph, statistics degrees conferred by level. So, this is data collected of individuals who have gotten degrees at the bachelor's, master's, and doctoral level in statistics. And what does the trend look like? Well, if you look at the red line in the graph, back in 1992, there were less than 1,000 people who graduated with master's degrees in statistics. And now, if you look all the way to the right of the graph, 2015, we have close to 3,000 bachelor's degrees. So that increase alone should show you the importance of why we need to learn how to use data. It is a highly sought out skill in any career path that you're going into. So you don't need to necessarily be in the statistics field as your major. If you're in political science, guess what? You have a ton of data, especially in an election year, on predicting the candidate that's going to win and making informed decisions for politicians. So there is a ton of reasons why data is important. The data explosion. Okay, so according to IBM, 2.5 exabytes of data are created every day worldwide, and more recent estimates has that as large as 5 exabytes per day. What the heck is an exabyte, you might say? Well, let me answer that. You might have heard of a gigabyte. Okay, so a gigabyte, you want to compare here on the left side of the chart. You can see that a gigabyte is that big, that big. A terabyte is 3 zeros bigger. A petabyte is 3 more zeros bigger. Exabytes are even bigger than that. So if you look at a gigabyte, which if you're familiar with any type of computer terminology, you most likely know about megabytes and gigabytes. An exabyte is 9 zeros. Okay, that is a billion, no, sorry, a million, a quantity of a million bytes bigger, a million times bigger than a gigabyte. Okay, so a billion bytes jumping up all the way to a quintillion bytes, which I rarely ever use that darn word, if ever. And we're saying that in a day, that's how many bytes are used through the internet. Crazy amount of data. So the data explosion, the world's data storage capacity over time. So you can see in the 90s, it's not the storage is not that big, but quite frankly, the internet wasn't a thing back then. Okay, so I'm old. Back then, we did not have the normal person did not have a computer. I did not have a computer for the majority of my childhood until I got to high school. Then I had that big blocky computer, and that thing had a DOS system in it, and you had to learn how to code DOS in order to do anything on your computer. There was no Windows or anything like that back then. Finally, when we hit the new age, the 2000s, and we started getting into the years of, okay, now we have Windows. Now we have Mac computers, Apple computers. We have systems, and we are able to access the internet quickly. Okay, back then it was dial up, and most of you probably don't even know what dial up is. But if you do, you know how incredibly frustrating dial up internet was. So once we got to this very high, fast system, the internet that you know today, look at the storage increase from just 2015 to 2020. 5 years, and there is a drastic increase in the amount of bytes that are being used over time. Okay, this is just giving you a snapshot on how quickly time has changed in just a short period of time, considering all these decades before where this was not a thing. So, when you apply statistical methods to increasingly larger data sets, there are very few data sets that you are likely to encounter that could challenge modern computers. Computers these days are so powerful, and there are some misconceptions about artificial intelligence. Uh, Many people believe that these AI systems, these robots, these self driving cars are replacing people's jobs. And that is not the case. They are supplementing, they are making us stronger and faster. But there is not an AI system that cannot exist without a human doing the updates and making sure that it fixes the break in the code, or maybe it encounters a situation that it can't adapt to. So a human needs to intervene. So it's not going to replace humans, it's just going to make us more efficient. Using current computing technologies, data sets that are feasible to process simple statistical models in a reasonable amount of time are on the order of terabytes. The moment that we get something bigger than a terabyte, we call this big data. So, big data is a loosely defined concept used to describe data sets produced by our globally networked, internet driven, sensor laden world. The most common meaning of a big data is a set of data sufficiently large to be challenging to analyze on a typical data center. And you'll see this when we use our statistical software, our Guru. We will be able to look at data, but our data sets will be quite small. Um, Most all of them will be quite small. And that's okay because we're just learning. I want you guys to be able to see the whole picture. And these large data sets, they're talking about using tens of thousands of servers and thousands of data storage arrays. And that might mean absolutely nothing to you. I just want you to be informed about what the heck is data and the different types of data that's out there, so that you're aware of how important what you're learning this semester is going to be. So, big data is essentially made up of four attributes, the four V's, okay, the volume of the data, the variety, the velocity, and the veracity. And again, this is just, you just need to know about big data on a surface level, just essentially that it's really big and complicated for one human to look at like an Excel spreadsheet is impossible. And that this is where computer analyzing is going, is to help us with data that is way bigger than one person can handle. Okay, and there's some really big sources for big data. Medicine's a huge source. Okay, physics, business is major source, and there are so many more. This is only a few sources. Okay, second half of chapter 1, sections 1.6 through 1.8. Now, I broke these up because the first half is very general intro to data and the ways data is being used and where data comes from. But the second half of chapter 1 is focused on more specific vocabulary words that you do need to know in order to be successful in this course. So the first one is population. It is very important that we know the difference between a population reference and a sample. So, a population is the collection of all outcomes, responses, measurements, or counts that are of interest. And a sample is only a subset or part of the population. So, for example, let's say that I wanted to do a survey on students' favorite professor at Northwestern or at the University of St. Joe's. I would then go, and if I wanted to do a population survey, that means I would have to ask every single student at the college I'm targeting. Every single one. I can't miss one. Population means everyone in your target. Now, if I'm targeting Northwestern Connecticut Community College, then I cannot grab a student from the University of St. Joseph's because they are not in my population. They're not in my target. So you have to make sure you have a well-defined population so that you know who it is you are talking about. Now, me surveying every single student at a college that I'm targeting is usually not that easy to do. I mean, think about it. You guys are students. Do you answer every email that comes out? I bet you don't. And that's just normal. Okay. If I wanted to survey everyone in a particular company, everybody in Cigna, it is not likely everyone's going to answer my survey. They're going to blow me off. So it is usually and much more commonly used a sample of the population. I would randomly select, let's say, 100 students at a particular college, and I would ask them my survey question. It is much more likely I'm going to receive all the responses to 100 of my surveys than to thousands and trying to target everyone. But just be careful and make sure that your sample truly fits your targeted population. So again, if I'm targeting all college students at Northwestern Connecticut Community College, then I can't sample a professor. They are not part of my population. They should not be in my sample. I can only select students that attend the college I'm targeting. Okay, let's look at this example. In a recent survey, 834 employees in the United States were asked if they thought their jobs were highly stressful. Of the 834 respondents, 517 said yes. Let's identify the population and the sample. Now I'm going to pause for a moment, or actually, you know what? Pause this video, and I want you to try this on your own. And then when you're ready and you think you have the answer, press play again. So the answer, the population here, is all employees in the United States. The sample is the 834 that were actually surveyed. Now, you might have said, oh, I see 834 and I see 517. 517 is a smaller number. That must be my sample. 834 must be my population because it's a bigger number. And I don't blame you for thinking that was the answer off the bat. That's how we were trained to think. We were trained to think very tunnel vision. But we have to learn, and that's why this chapter is so critical to our understanding of statistics, how to think beyond the words. So when I'm reading this in a recent survey, 834 employees in the United States. That sentence alone is all I need to discern what is the population and what is the sample. So if you think about it, they didn't use a sample, they didn't use the word sample. They didn't say they sampled 834 employees. They didn't specifically state that 834 employees is some of the employees in the United States. It's based on logic. We are talking about real world examples, everything that we work on in this class. So when I read this, if they're talking about employees in the United States, I have to logically know that there are way more than 834 of them. We have millions of people in the United States. So we know there are more than 834 people working in the United States. So that's how I identified, oh, they are targeting employees in the United States. And then they sampled 834 employees in the United States. Another definition, a frame. So a frame is a listing, it's a list containing all members of the population. So for example, if I was targeting a college and I wanted all the students enrolled or registered at that college, then my frame would be a list of all registered students. The word census is used as a survey that includes all the elements or units in the frame. So essentially including the population, not a sample. You probably heard the word census before, as we have this, it came out this year. Every 10 years in the United States, a census is sent out to every single citizen in the United States, and it is by law required for us to fill it out. Not that any consequences ever happen when you don't fill it out, but it's important for them to collect that data. It's about demographic data, our race, our income, and they're trying to identify certain population sets. Okay, two more very important vocabulary words are population, excuse me, parameter and statistic. So what's great is parameter starts with a P and it describes a population. So it is a characteristic of a population. And statistic starts with an S. And that's great because it's paired up with a sample. It's a characteristic of a sample. So an example of a parameter, let's say that I marched my way up to the registrar's office and I asked for a list of all registered college students' GPA. Well, I wanted to find out what is the average GPA for all college students at this particular university. I would then add up all of the GPAs for every single registered student. I would then divide by how many there are, and I'd come up with what's called an average, or in statistics, we're going to learn is called the mean. Now, this average, this number that represents the average GPA of all college students registered at this particular university, is called a parameter because that average is a characteristic of the population. It describes, it comes from a calculation of all students. Now, let's say I did not have access to all the students' GPA. Well, then I would need to get a sample. Now, the easiest sample for me as a professor would be my students. So let's say that I gathered all the GPAs from every student registered in my classes. This is a sample of students from a targeted population of college students at a particular college. Now I add up all the GPAs of my students and divide by how many I have to get an average GPA. Again, it's still an average GPA. It looks very similar to the parameter I just calculated. But this average GPA I calculated only was calculated from some of the registered college students at this college. So that's why that average GPA would be labeled a statistic because calling it a statistic tells you every single person in the targeted population was not used to calculate this number. Let's look at this example. A survey of several hundred collegiate student athletes in the United States found that during the season of their sport, the average time spent on athletics by student athletes is 50 hours per week. Now, we want to decide whether this number 50 hours per week that was calculated? Is it a parameter because it was calculated from a population? Or is it a statistic because it was calculated from just a sample? Again, please pause this lecture, think about it for a moment, come up with your own answer, and then press play again. So the answer will be that this is a statistic. 50 hours per week was not calculated from all collegiate student athletes in the United States. It was only calculated from several hundred. And logically speaking, there are several hundred athletes at one university at any time. So it's fair to say that if we're considering all universities that have college athletics, that you're going to have way more than several hundred. So this would be a statistic. Another example, the freshman class at a university has an average SAT math score of 514. This a parameter? This SAT score of 514, is it a parameter calculated from an entire population or is it a statistic? The answer is it's a parameter. Why is it a parameter? Because the target population was not all college students at this university. The target population was the freshman class. Notice of the wording, it didn't say some of the freshman class. It didn't say 25 students of the freshman class. It didn't say the freshman class out of all college students. It just said the freshman class. So that reference, the, is an entirety, and it's talking about targeting a freshman class. And therefore, that's how we recognize that freshman class was the target population. And it was not some of these freshmen, it was all of them, hence the word the. And that makes 514 calculated from every single freshman in the class, and it would be a parameter. Next example. In a random check of several hundred retail stores, the FDA found that 34% of the stores were not storing fish at the proper temperature. Kind of gross, but totally possible. Is the number 34% that was calculated considered a parameter or a statistic? The answer is a statistic. So again, we look back in the wording, we look for what is being targeted, what is our population, and our population is retail stores. Now, it's a little fuzzy in this problem because they don't tell you in the United States, in Connecticut, so it's a little hairy on several hundred. Is that all of them? But when you have a number like several hundred, 834, that's typically a defined set or sample of something bigger. So if they wanted to use all the retail stores and make it clear that it was a population that was used, they would have to use wording like the retail stores or all retail stores in order to clarify that it was the entire population. So since it was just several hundred of them, that's why 34% is a statistic. Now, in statistics, there are two branches. There's something called descriptive statistics, and then there's another branch called inferential statistics. The majority of this course is in the descriptive end. That is almost everything that we're going to be doing. The data collection, the organizing the data, the summarizing, and the displaying. So tables, charts, averages, all that stuff, all descriptive. And the reason why it's descriptive is because it's all referencing the sample. Now, why do we collect samples and do all this stuff? Well, it's so we can make decisions about the population. So when in an election year, when you find that there's exit polls going on all the time to predict who's going to be our next president, well, those sample of 1,000 people in those exit polls are used to make predictions on who is 51% of the voters are in favor of which candidate, 49%. All those numbers are coming from samples, but then they make predictions about who's going to win the election in the entire United States election, even though they've only sampled 1,000 citizens. So Descriptive statistics, they can tell you the exact amount in the exit poll. Everything talking about anything to do with that exit poll is descriptive. But the moment that we jump over to inferential is when we make a very big, bad, broad statement like, this candidate is going to win the election. And I'm purposely keeping this generic so that we aren't calling out or talking about politics in this class with specific names. So, some examples of descriptive statistics would be using mean, median, mode, range variance and standard deviation, a frequency distribution. These probably don't make any sense to you, and that's okay. These are things that we're going to cover over the next couple chapters. Here's an example. A study of 2,560 US adults found that the adults not using the internet, that of the adults, excuse me, found that of the adults not using the internet, 23% are from households earning less than 30,000 annually. So if you look at the figure on the right, it's showing that these are the percent of adults who do not use the internet based on the income in the home. So incomes less than 30,000, you have 23% of those households that do not use the internet. In income housing 30,000 to about 49,999, 12% of those homes don't use the internet, and so on. So we can see that it seems to correlate that the more money you make, the less households that are not using the internet. So one might make a broad statement stating that low income housing cannot afford the internet. Now, personally, I don't think that's a fair statement because the data says only 23%, less than a quarter of low income housing doesn't have the internet. That to me does not say that people who have make less than $30,000 a year can't afford the internet. That's not a conclusion I would make, but that's a fair point for you to start thinking about. How many times have you guys read on the internet these broad statements? This sugar causes cancer. Holding the phone up to your ear causes cancer. This and that, all of these broad statements that you're like, oh my gosh, is that true? Well, what does the data say? One of the studies that was done quite a while ago was one of those artificial sugars, and I can't remember which one at the time, at the moment. But there was a statement of, oh, this artificial sugar causes cancer, stop using it. And people freaked out. They boycotted the sugar. They switched to real sugar or they went to a different artificial sugar. And I was super curious, like, really? What is the evidence? What is the data that led to the inferential conclusion that this particular artificial sugar caused cancer? So I looked it up. You would have to ingest 2 pounds of that artificial sugar a day. A day. Who takes in 2 pounds a day in order for you to show signs of causing cancer? Realistically, any product that you ingest at large amounts is most likely going to cause some complication. So these are the things I want you to think about. If anything, by the end of this course, I want you to read the world differently. I want you to not just take things for face value. I want you to think. I want you to ask questions, which we're going to get to in a little bit. Another example, a study of 300 Wall Street analysts found that the percentage who incorrectly forecasted high tech earnings in a recent year was 44%. Now, everything stated in this example is descriptive statistics. We're referencing a sample of 300 Wall Street analysts, and we are talking about a statistic, 44%, based on the sample. Now, the moment that I jump over to inferential statistics is when I make a broader prediction based on the sample stuff that I calculated and say that not even the analysts get it right. Okay, so that's something I'm talking about all analysts now. And based on the data, I'm saying, hey, not all of them are going to forecast correctly. That's inferential statistics. Again, that's what you read all the time and hear all the time on the news are these broad statements that are based off of some data. And you have to remember your conclusions, if you actually saw the data behind those statements, may not be the same conclusion that you're hearing on the news or the internet. Now, the last part of this chapter is about statistical literacy. So these are the questions that I was talking about. By the end of the semester, I want these questions to be second nature for you. I want you to read anything on the internet and be like, where did the data come from? It's really important to know where the data came from. For example, if I wanted to know how students thought of me as a teacher, and I simply went up to their face and said, hey, what do you think about me as your teacher? And then every student who I still have their grades in my hand because it's the current semester, all say, oh my gosh, you're great. Is that an accurate survey? If I say, oh, 100% of my students think I'm an excellent teacher, but I didn't tell you how I collected the data. I didn't tell you I asked them face to face while they were currently my student and I held their grade in my hand. Would you, would my validity of my outcome, would that change if you knew that how I collected the data? Well, I surely hope so. In order for my data to be accurate, I would need to set out I would have to hire a third party, a person completely disjointed from our course, to survey my students and let my students be anonymous so they know that their answers to the survey will not affect them in any way. That would make a whole difference in believing the outcome of that survey. Other questions you should ask. How was it sampled? And is the sample large enough? Imagine if I asked two students what they thought of me and then said 100% of the students like Professor Wiggins. How accurate is that if I only asked two students and I'm trying to represent 1,500 students at a college? I'm pretty sure people would not believe me anymore if they knew I only sampled two. So you have to think about that when you're reading things. How many people were asked? Was it just a handful of people? Because that's not very valid. Or was it hundreds or thousands of people? How reliable or accurate were the measures used to generate the reported data? Are the reported statistics appropriate for this kind of data? How about the graph? Is the graph drawn appropriately? Okay, all of these questions, and I'm not going to go into detail for each one because these questions are the questions we'll be asking all semester and learning how to figure out where this data came from and is it valid? Is it good data? Should I trust the results? Um, Hold on, I'm trying to get center mode and my mouse is being weird. Okay, so that is chapter one. I hope you enjoyed our first lecture. And if you have any questions on any of this material, feel free to reach out. See you next time.